Dear students, this is Dr. Biju Vasudevan. In this video, we will discuss chapter 12.5 Sturm Liouville problems. Right, introduction. See, for convenience, we present here a brief review of some of the ordinary differential equations that will be useful throughout this chapter. See, when we start solving exercise problems, we will encounter some differential equations of this form. And again, we don't need to solve them. We have already seen the answers of this kind of differential equation in our previous courses, like elements of differential equation, isn't it? So if you have seen such a differential equation in any of the exercises coming up, you must know what is the answer of solution for the differential equation. This is Cauchy-Euler equation, and the solution is on the right side. And we know Bessel's function. This is Bessel's differential equation. The solution is in this form, and Legendre's equation, and there are multiple solutions of this form, isn't it? Okay, this will be useful in the exercise problems, so remember it. Okay, let's start with one more point. To come to the general solution, y double dash minus y a square y is equal to 0, will in the future employ the following informal rule. This form of the solution will be used when the domain of x is an infinite or semi-infinite interval. Or this form of, there are two forms of solution for this case. Come back here. Here there are two forms of solutions. First one will be used when, for this differential equation, when the solution falls in finite or semi-infinite or infinite intervals, right? Otherwise, if it is a finite interval, you will use this solution. That's what given here. Now we are moving to the concept Sturm Liouville problem. What is Sturm Liouville problem? Sturm Liouville actually is the name of two different mathematicians, Sturm and Liouville. The differential equation that can be expressed in this form. We will see some examples in this chapter. When you expand this one, you will understand, or this says that you apply product rule, and r dash y dash plus r y double dash, that's it, and lambda times p plus q times y is equal to 0. These two together becomes this single term, isn't it? Because using product rule, you can expand it. So any differential equation that can be expressed in this form, equation number 1 form, is said as Sturm Liouville problem with some boundary conditions. We should have some boundary conditions. So here, see, in this differential equation, r, this term r, this term p, this term q are functions of x, and this equation is called Sturm Liouville eigenvalue problems. Eigenvalue problem, some books will address is Sturm Liouville boundary value problem, right? Eigenvalue problem or boundary value problem, SLBVP or SLEVP, both are okay. In the interval, in the closed interval a and b, satisfying the boundary conditions, this one, boundary conditions a1, you can call it alpha 1 y of a, alpha 2 y prime of a. Its first boundary condition deals with the lower limit of the interval y at a, y prime at a. The combination is, linear combination is equal to 0. Second boundary condition deals with the upper limit of the interval. So from the boundary conditions, you will understand what is the lower limit and the upper limit of the function. And another information, all the constants are real numbers, alpha 1, alpha 2, alpha beta 1, beta 2, but both of alpha 1 and alpha 2 cannot be 0. One of them should be non-zero. Similarly, beta 1, beta 2 both cannot be 0. One of them should be non-zero. So there will be a condition for this one, alpha 1 square plus alpha 2 square not equal to 0. When you sum the squares of these two terms, it should not be 0. Okay, that's what we find here. Now, many differential equations such as Legendre's equation, Bessel's equation can be expressed in Sturm Liouville form. Some more information. Obviously, y is equal to 0 is the solution of this problem. You can check in this problem. Y is equal to 0. When you put y equal to 0, it will satisfy this equation number 1. So y is equal to 0. It's an obvious solution. So as far as the solution of differential equation is concerned, to finding y is the purpose. Y is equal to a function of x or function of t. That will be our solution, isn't it? So y equal to 0 is a solution, obvious solution for any value of the lambda, which is a trivial solution. So we call it trivial solution. So the purpose of this problem is to find non-trivial solution. We are looking for non-trivial solutions. So any other non-trivial solution satisfying the boundary condition is called eigenfunction of the problem, and the corresponding lambda value for which we will get a non-trivial solution is called, that is, the lambda is called eigenvalues of the problem. So the purpose of this solution for procedure is to find a non-trivial solution which is an eigenfunction for a Sturm Liouville problem. Okay, and if you put r is equal to 1 and p is equal to 1, q is equal to 0 in this equation number 1, go back, check in this equation. R is 1 and p is 1, q is 0. What do you get here? R is 1, so y prime whole prime, y double prime, and p is 1, q is 0, is lambda y is equal to the very simple form of Sturm Liouville problem, y double dash plus lambda y is equal to 0. That's what they come to say here. The simple, we get y double dash plus lambda y is equal to 0, and take there are two conditions, isn't it? Alpha 1 y of a plus alpha 2, isn't it? Here alpha 1 plus y of a, alpha 2 plus y prime of a, y prime of a, y prime of a, which is equal to 0. Second, beta 1 y of b plus beta 2 y prime of b is equal to 0, isn't it? So in these two boundary conditions, you take alpha 1 and beta 1 is equal to 1. These two parts are considered to be zeros, alpha 2. So second part is 0. So you get simple boundary conditions. Y of a is 0 and y of b is equal to 0. So boundary condition, at least one boundary condition will be there for lower limit and one boundary condition will be there for upper limit, right? Because both the alphas cannot be zeros, similarly both the betas cannot be zeros. So these are the boundary condition example given here, a trivial version of that, a very easiest version of the Sturm Liouville problem. If yn of x and ym of x are two different eigenfunctions of the Sturm Liouville problem, then they are orthogonal with respect to the weight function p of x. And we have seen in the previous chapter what is orthogonal. We have to find inner product of yn of x and ym of x, and the answer should be 0 for functions from a to b. You can integrate for continuous functions with respect to p of x, yn of x, ym of x dx is 0, right? So this method we have seen. So when you find yn of x, ym of x are two different eigenfunctions of a Sturm Liouville problem, then they are orthogonal. That's the beauty here. Here the solutions of the differential equation are going to be pairwise orthogonal with respect to a weight function p. Most of the time weight function will be 1. There are some occasions where p is not 1 as well. So that's what given here. So that is relate to be p of x, yn of x, ym of x equal to 0 for m not equal to n. Also the norm of the eigenfunctions are equal to 1. that is inner product of the function with itself. Okay. An SL EVP is called regular if P is greater than 0 and R is greater than 0 on this interval. Let's talk about the function y double dash plus lambda y is equal to 0, and in the interval 0 to 1, y of 0 is 0, y of 1 is also 0. This gives A is 0, B is 1. First boundary condition will give lower limit, second boundary condition will give upper limit 1, isn't it? So the interval is 0 to 1. Now think of it this one. Here the P value and R value are equal to 1, Q is 0. We have assumed from the original function. Now check everything here. This is regular or not? Yes, in the boundary condition R is greater than 0, P is greater than 0, obviously this is regular. This SLEVP, Sturm Liouville eigenvalue problem or boundary value problem is called a singular. This is called singular if P is positive in the interval open interval a b and P of A is 0. P of A is non-zero here. P is constant given as 1. P is 1, so P of A 0, P at x value is 0 because P is a function of x, is still 1, so this condition is a failure, isn't it? So if the condition is true, then we will say the function is this problem is a singular problem. And what's next? There are certain conditions. If the conditions are satisfied, P of A and P of B are equal, yes, both are positive, and B, P and R, then P, Q are continuous in functions of x on the interval closed interval a b, then this problem coupled with the boundary conditions is called a periodic Sturm Liouville EVP. You can check the only additional condition that you have to check is P of A is equal to P of B. That is true here in this case. So this is periodic Sturm Liouville EVP. And some more information. Y of A should be Y of B. That is not true. It's true. Yeah, true. Y prime is also equal. That is right. All the conditions are true for this case. Now an example how to identify whether a differential equation given is a Sturm Liouville problem can be expressed in Sturm Liouville form. This is Bessel's differential equation, isn't it? A form of differential equation which is in Bessel's form. Okay, divide this equation by x. Here x will be, the degree of x will be reduced, x y double dash. Here x will be removed, and this function becomes a square x minus v square over x times y equal to 0. Now let this r is your this x is your r, and p is also x. Where is p? It should be the coefficient of lambda, isn't it? Lambda is a square, this term is lambda. Now rewrite this one. What do you get? This one, these two can be written as x y dash whole dash, isn't it? Check your product rule, x times y double dash. Now y dash times, when you differentiate x, it will be 1. So the product rule of these two will give you this one. So x y dash plus, here a square is lambda, lambda p is x, minus v square over x has been taken as q, plus q. Y is 0. Now this is r, ry double, ry prime, ry whole, ry prime whole prime, isn't it? And the lambda p plus q times y is 0. This has been expressed in Sturm Liouville problem. So this way we can modify the given differential equation so that it can be expressed in Sturm Liouville problem. And this form we call the differential self adjoint form. because this is also Sturm Liouville form. But when you club the first two terms using the product rule, it will be called a self-adjoint form, right? Some properties have been listed here. There exists an infinite number of real eigenvalues that can be arranged in increasing order. Such that the last lambda n approaches infinity when the number of eigenvalues goes to infinity. For each eigenvalue, there is only one eigenfunction. If lambda 1 is there, there will be one y1. For lambda 2, we will find only y2, except for non-zero constant multiples. That's okay. Eigenfunctions corresponding to different eigenvalues are linearly independent. A linear combination of them will be 0, lambda 1, lambda 2, y2, isn't it? So you can take some constant a1. We're talking about eigenvalues, eigenfunctions. A1, y1, a2, y2, some constant an, y1 equal to 0. It gives all constants are zeros, isn't it? That's the concept of linearly independent. The set of eigenfunctions corresponding to the set of eigenvalues is orthogonal with respect to the weight function. This we have already seen. The solution of this kind of Sturm Liouville problem are pairwise orthogonal with respect to the weight function p. P is also there in the given function. P is the coefficient of lambda, isn't it? Okay. Now self-adjoint form. So if you get a differential equation in this form, or the first two terms can be clubbed to this form. This is a self-adjoint form, isn't it? Actually, we are here. We have not given. We have given an example here. So when you turn this down, you can write r of x y prime whole prime plus that will give first two terms, and then lambda p plus q y is equal to 0, where every r, p, q are functions of x. So this form is called a self-adjoint form. Right. Fine. Now we are moving to exercises. We should remember the solutions of different differential equations that we have seen in the first page. Okay, let's start with this exercise. What we want to do first, read the question carefully. Find the eigenfunctions and the equation that defines the eigenvalues for the given boundary value problem. This is a Sturm Liouville boundary value problem. We have seen it, isn't it? Because you can obviously check this formattation. Sometimes in the questions they will ask you to verify whether this is Sturm Liouville problem. So you have to identify what is R, what is P. R is 1, P is 1, Q is 0 in the given R y dash whole dash plus lambda P plus Q of y is equal to 0. Substitute them. R is 1, then y double dash you get first term. P is 1, Q is 0, it will be lambda P, lambda y is equal to 0. In the boundary conditions, you understand the lower limit is 0 because both the terms are involving 0. Here upper limit. So the interval is 0 and 1. That is A is 0, B is 1. Alpha 1, alpha 2, beta 1. Isn't it? Alpha 1 is 1, alpha 2 is 1, beta 1 is 1, beta 2 is 0. So we understand that this is a Sturm Liouville problem. Okay. Now how to solve this one? For the what's the question? Eigenvalues for the given boundary value problem. Find the eigenfunctions. Solve it, isn't it? Give the eigenfunctions corresponding to these approximations. Okay. What we are going to do is on the separate sheet we will do it. Okay, I'll do it on a separate sheet. I will rewrite the function y double dash plus lambda y is equal to 0. And here what we are going to assume is 3 cases for lambda. First one is lambda is negative, and then lambda is equal to 0. Third case, lambda is positive. And for all these 3 cases, we are going to analyze whether there is a non-trivial eigenfunction, non-trivial solution exists or not. When lambda is negative, we have to let lambda is negative mu square. Mu is another constant, isn't it? So whatever the value of mu, negative or positive, since mu square is with a negative sign, lambda will be always negative. We assume lambda is negative mu square. Therefore, the equation 1 becomes y double dash minus mu square y is equal to 0. And from the front page, you can find the solution of this problem as, so mu is allowed to take any value between negative infinity and positive infinity, isn't it? Okay. The solution for this one, by solving a differential equation, find you can, if you don't want to see the first page, you can go ahead and find the auxiliary equation, and then find there are 3 different cases of solution. Here the solution of this kind of differential equation will be y is equal to c1 e raised to the constant m1 minus mu x plus c2 c2 e raised to plus mu x. For your reference, first time I will show you, but and every time I will not. Okay, this is the auxiliary equation is m square minus mu square is 0. This is called auxiliary equation. We will write y double dash becomes m square and y will be 1. Mu square is mu square, isn't it? This gives you m square is mu square. M is plus or minus mu. So m1 is positive mu or negative mu, m2 is positive mu. Therefore the solution is y is c1 to e power m1x plus c2 into e power m2x will give you this solution, right? And the next time onwards you should be careful. There are some solution in the first page, you can directly use them. Now we have to use the boundary conditions. What are the boundary conditions? Boundary condition 1 given in the problem is y of 0 plus y prime of 0 is equal to 0. Y of 1 is equal to 0. This is second boundary condition. This is boundary condition 1. This is boundary condition 2. Okay, we want y prime. We have only y, so differentiate y, get y prime. What is y prime? c1 into e power minus mu x into minus mu, isn't it? Minus mu plus c2 into mu e power mu x. This is your y prime. Okay, we want y of 0 and y prime of 0. Y of 0, what is y of 0 is 0, gives, take here x is 0. In this equation take x equal to 0. X e power 0 is 1, e power 0 is 1. c1 plus c2 is equal to 0. This is result number 1. Y prime of 0 is 0. What do you get? Y prime of 0 is 0. In this equation take x equal to 0 minus mu c1 plus mu c2 is 0. This is second result. We have to club these two results because boundary condition 1 says the sum of these two is equal to 0. So this one, c1 times 1 minus mu plus C2 times 1 plus mu is equal to 0. When you club these two results, you'll get this one, isn't it? Second condition, y of boundary condition 2 y of 1 is equal to 0. In this equation of y, substitute x is equal to 1. You get c1 e raised to minus mu plus c2 e raised to positive mu is equal to 0. These two are very important results, 2 and 3, from which we are going to find the values of c1 and c2. Okay, the next page, I will repeat the boundary condition here. C1 times 1 minus mu1 plus C2 times 1 plus mu is equal to 0, not mu1 is mu. Second boundary condition is, this is equation number 2. Second boundary condition is what? C1 e raised to minus mu plus C2 e raised to mu is equal to 0. And to solve such a kind of two equations, we can use any method. I just use the coefficient matrix form. I can write this one as 1 minus mu 1 plus mu, the coefficient of C1 C2 in the first row, e minus mu e power minus mu e power mu multiplied by C1 C2 is equal to 0. We can mathematically verify this determinant is non-zero for any finite value of mu, because exponential will be 0 for only infinite values, isn't it? Exponent e power negative infinity. So this determinant is non-zero. Determinant of this 1 minus mu 1 plus mu e raised to minus mu e power mu is non-zero. This gives C1 and C2 should be 0. That is C1 equal to 0 and C2 equal to 0. What we get from this conclusion, the determinant cannot be 0. So the product of two elements are 0. Therefore second matrix should be a 0 matrix. C1 and C2 should be 0. Right. So when you get C1 C2 value, we should use the y equation. What is y? Y is C1 into e power minus mu x plus C2 into e power mu x. Using C1 and C2 equal to 0 in y, we get y is equal to 0, which is a trivial solution. Therefore lambda negative 0 is not an eigenvalue, because eigenvalues are those values corresponding to those values you get eigenfunctions, non-trivial solution. Eigenvalues are the values corresponding to the non-trivial solution, not for a trivial solution, right? So this is not an eigenvalue. So we are done with the case lambda less than 0. Now we are going to check lambda equal to 0 for the differential equation y double prime plus lambda y is equal to 0, isn't it? Put lambda is equal to 0, we get y double prime is 0. This is a very easiest form of differential equation, whose solution is c1x plus c2. When you differentiate it twice, you get 0, isn't it? So solution method is available in the first page. You can check why the solution of this differential equation y equal to c1 c2. Again we are going to find the values of c1 c2 by using the boundary conditions. For boundary condition we need 3 information. What is y prime? This will give y prime. Y prime, differentiate y with respect to x, you will get y dash is c1, isn't it? Y dash is c1. C2 will be 0. When you differentiate x, it will be 1. Now boundary condition 1 involves two terms, y of 0 and y of y dash of 0. What is y dash of 0? Is y dash of 0, whatever in y dash, the answer is C1. Y dash of y of 0, when x is 0, it will be C2, y of 0. So I'm writing, okay, sorry. Using x is 0 in y. Using x is 0 in y, you'll get y of 0 is equal to C2. Using x equal to 0 in y prime, you get y prime of 0 is C1. Now boundary condition 1. What is the boundary condition 1? Y of 0 plus y prime of 0 is equal to 0. What is your y of 0? Go back here. Y of 0 is C2, y dash of 0 is C1. So this is C2 plus C1 is 0, which gives C1 is negative C2. One where constant is the negative of the other. Now second boundary condition. What is second boundary condition? Y of 1 is 0. Y of 1 is boundary condition 2. We need it or not, we'll check. Y of 1 is 0. In this equation, take x equal to 1. Again you get C1 plus C2 is 0. So it's enough. Both are representing the same equation. C1 plus C2 equal to 0. So one constant is the negative version of the other constant. Use this in the equation of y. Y is C1x plus C2. We can make C2 is negative C1. So you will get y is equal to C1x minus C1. Therefore y is equal to C1 is taken common, x minus 1. This is the eigenfunction. This is non-trivial solution, not 0. 0 is called a trivial solution. Therefore this is an eigenfunction. Therefore lambda is equal to 0 is an eigenvalue. That's it. So you can simply write, giving some value for C1 as 1, you can write y is x minus 1. So this is the first answer for lambda equal to 0. Now we want to analyze the third case. Third case is for lambda greater than 0. And the differential equation you should recall y double dash plus lambda y, and lambda y is equal to 0. Now for lambda is to be positive, let lambda is mu square. Whatever the mu value, when you square it will be positive. So what is the different solution of this differential equation? It will give the auxiliary equation becomes m square plus mu square is equal to 0. So m square is minus mu square. M is plus or minus I mu, isn't it? So in this case, this kind of cases are alpha plus I beta, alpha minus I beta type solutions. Alpha is 0, beta is mu, isn't it? So this kind of complex pairs will give you solution y is equal to e raised to alpha x, a cosine beta x plus b sine beta x. So in this case our solution is y e power alpha, there is no alpha here, so e power 0 will be 1, c1 cosine mu x plus c2 sine mu x, and then we got this one. Okay, this is our y, from which we need to find some values of c1, c2. by using the boundary conditions. Now recall the boundary condition 1. What is it? Y of 0 plus y prime of 0 is equal to 0. This is boundary condition 1. Second boundary condition, y of 1 is 0. We are in the interval. Actually everything is going on in the interval 0 to 1. Okay, because from the first boundary condition we know x is 0, x is a, from second one is 1, and okay. What is y of 0? We want y and y prime. From this one find y prime, differentiate it to find y prime. Cosine, when you differentiate cosine, it will be minus sign, so minus c1 sin mu x times mu, there is a mu as well, plus c2 mu cosine mu x. Okay, therefore we can rewrite y prime is minus c1 mu sin mu x plus c2 mu cosine mu x. This is y prime. Now we have both y and y prime. We can find all terms for the boundary conditions. Come on, what is y of 0? Put x equal to 0 in the first value of y. Cosine 0 is 1, sin 0 is 0. It will be c1. What is y of 1? Put x equal to 1. Cosine c1 cosine mu plus c2 sin mu, x will be 1. Now what is y prime of 0? That is coming in the boundary condition, isn't it? Y prime of 0. Put x equal to 0 here. Sin 0 will be 0, cosine 0 will be 1. It is c2 mu. Now we have to club these two. Y of 0 plus y prime of 0 is equal to 0. So c1 plus c2 mu is equal to 0. So boundary condition 1 gives c1 plus c2 mu is equal to 0. Therefore boundary condition 2 will give you what? Go back and check. This one, y of 1 is 0. This one should be equal to 0. c1 cosine plus c2 sin should be equal to 0. c1 cosine mu plus c2 sin mu is equal to 0. When you write this in matrix form again, the coefficients of c1 c2 here are 1 and mu. Here the coefficients of c1 and c2 are cosine mu, sin mu, and this matrix multiplied by c1 and c2 is equal to 0. 0 matrix, 0 row, 0 column actually. So for this, if the product of this one 0 on whether this can be 0, for this non-trivial solution exists if this determinant is 0. Non-trivial solution exists if and only if the determinant 1 mu cosine mu sin mu is equal to 0. If the determinant is non-zero, obviously c1 c2 should be 0. c1 c2 should be 0 is a trivial solution. So let's verify whether the determinant is possibly 0 or not. If this is possibly 0, then that will give you a non-trivial solution. It is possible to get this determinant 0. That is, cross multiply sin mu is equal minus mu cosine mu is equal to 0, which is sin mu is equal to mu times cosine mu. Divide by cosine mu on both the sides. Divide by cosine mu. You will give sin by cosine, it is tan mu, which is equal to mu. The right answer there will be only mu. And what is mu? We have assumed at the beginning of this case that lambda square is mu. Therefore, mu square lambda is equal to mu square. Therefore, mu is equal to plus or minus root lambda. As we are looking for positive value of lambda, it will be positive. So we can write tan root lambda is equal to root lambda. So any value satisfying this equation is a solution of this matrix, isn't it? Non-trivial solution. Therefore, any value satisfying this equation will give us a non-trivial solution for the given differential equation. Therefore, y lambda is equal to mu square is an eigenvalue. So this determinant is not always non-zero. This is possible to be zero when this equation is satisfied, isn't it? So we are concluding this problem by telling that lambda mu, which is mu lambda, which is mu is equal to root lambda is an eigenvalue. So we know C1, C2 cannot be 0 sometimes in this case. So what is the y we found? Y is C1 cosine mu x plus C2 sin mu x was the solution of the differential equation for this case, and we can take here mu is equal to root lambda. So y is equal to C1 cosine positive root lambda x plus C2 sin root lambda x, and we have a boundary condition called C1 plus C2 mu is equal to 0. Check that one. Take one of the values as negative 1. Take C2 is negative 1. You'll get C1 minus mu is equal to 0. So C1 is positive mu. We can substitute the value here in this equation, get the final value. Generalize, we will generalize it as yn. C1 is mu cosine root lambda x. Further, you can replace the mu value as root lambda. C2 is negative, so negative 1 we assumed, sin root lambda x. So everything in lambda. Yn is equal to root lambda cosine root lambda x minus sin root lambda x. This is an eigenfunction. Is an eigenfunction for which the eigenvalues are root lambda, isn't it? That is satisfying the condition tan root lambda. So any value of root lambda that satisfying this equation is an eigenvalue for which we will find eigenfunction in this form. Thus the end of this problem. Now let's go to the next problem from the PowerPoint. This has been solved. The next problem is coming up. The answer you can verify here. We have been given another function y double dash plus lambda y is equal to the similar type Sturm Liouville problem, subject to the periodic boundary conditions y of minus L is equal to y of L. So the limits are minus L and positive. Show that the eigenfunctions are, we have to show that these are the eigenfunctions, isn't it? We will have to check this, and we know this set is orthogonal in the interval minus L to L. We have proved it in the previous sessions. Okay, now we have to find the solution for this one. Y double dash plus lambda y is equal to 0. Boundary conditions have been given here, two boundary conditions. Let us start in the separate sheet. let me write the problem. Y double dash plus lambda y is equal to 0, and boundary condition 1 BC1 is y of minus L is equal to y of L. Second boundary condition has been given as y prime of minus L is equal to y prime of L. So the limits, the boundary is minus L to positive L. In the closed interval, everything is going on, right? Okay. As usual, there are three cases. Lambda negative. First case, lambda is negative. Therefore, let lambda is negative mu square. So what happens in this? It will be y double dash minus mu square y is equal to 0, and the solution should be predetermined known on c1 e raised to mu x or minus mu, as you choose, mu x plus c2 e power minus mu x. Okay, now we should use, we need to find y of L, y of minus L, y of minus L, and equate them to get y of minus L, y of minus L. Substitute x is negative L, so you get c1 e raised to minus mu L plus c2 e raised to mu L. X is negative L. This is y of negative L. And obviously, what is y of positive L? This will give boundary condition when you equate this one. C1 e raised to mu L plus C2 e raised to minus mu L. These two together will get you boundary condition 1. Boundary condition 1. Equate them. C1 e raised to minus mu L plus C2 e raised to mu L is equal to C1 e raised to mu L plus C2 e raised to minus mu L. This is our first conclusion about the boundary condition 1. Let's talk about second boundary condition, and we need y prime. Differentiate y. Get y prime. Y prime, yes, when you differentiate y, c1 e raised to mu x times mu, and second term has negative, so negative c2 mu e raised to minus mu x. This is our derivation of y. Now y prime of L will give you c1 mu e raised to mu L minus c2 mu e raised to minus mu L. Similarly, second term for the boundary condition, first term has been done, second term is y prime of negative L. What do you get? Y prime of negative L. Substitute x is negative L in this equation, so you will get c1 mu e raised to minus mu L minus c2 mu e raised to mu L. Now when you club these two, you will get your second, when you equate these two, you will get your second boundary condition. You will write boundary condition 2 gives, what is it, c1 mu e power minus mu L minus c2 mu e raised to positive mu L is equal to c1 mu e raised to mu L minus C2 mu e raised to minus mu L. This is the conclusion from boundary condition 2. Now using this one we can judge whether C1, C2 can be only zeros or non-zeros. Okay, now we will rearrange boundary condition 1, the next page, taking C1 one side, C2 is the other side, right? So boundary condition, from boundary condition 1 we are rearranging the terms to meet C1 terms on the left side. See, go here, this is quotient of C1, here this is quotient of C1. When it is in the left side, this will be negative sign. So you will get that e raised to minus mu L minus e raised to mu L on the left side. On the right side everything will be C2, though you will get, then check, e raised to minus mu L minus e raised to mu L positive. See, these two terms are looking equal, so divide by the same term. This will give you C1 is equal to C2 from the boundary condition 1. Similarly, let's rearrange boundary condition 2. Let's check boundary condition. C1 should be kept in one side. So this will be C1. Bring it to left side. This will be C2. Take it to right side. So C1 will give you mu. C1, when you take C1 mu, you can take outside. C1 mu can take outside. From this one you will get e raised to minus mu L minus e raised to positive mu L. E raised to minus mu L minus e raised to positive mu L. In the right side, C2, along with the C2, what else you will find? C2 mu. This will be positive, isn't it? In the right side. E raised to, okay. C2 mu. E raised to positive mu L. Is it? Minus e raised to minus mu L. So e raised to minus mu L. So rearranging will give you negative sign. The right side. Left side is C1 mu e raised to minus mu L e raised to positive mu L, isn't it? Here C2 mu e raised to minus mu L e raised to positive mu L will give you a negative sign in front. Now this can be divided by mu times e raised to minus mu L minus e raised to mu L. You get C1 is negative C2. C2 is our first conclusion, but another conclusion is C1 is equal to negative C2. These two are possible only when C1 and C2 are zeros. Otherwise, they cannot be, both cannot be true, isn't it? So C1 and C2 are 0 in the first solution of y. What is y? Y is C1 e power mu x plus C2 e power minus mu x. C1 and C2 equal to 0 gives y equal to 0 a trivial solution. So there is no eigenvalue. This is solution, trivial solution. Second case, obviously lambda is 0. So y double dash is 0 gives y is equal to C1x plus C2. Now we gotta use the boundary conditions again to check whether any eigen function is possible or what. And what is y prime? Y prime is C1. We have all these terms. Now initial conditions, y of minus L. Y of minus L is, from this one x is negative L, so minus C1 L plus C2. Y of L, C1 L plus C2. And y prime of L is C1. Y prime of negative L is also C1 from this one. Since y is constant function, whatever the value of x, you will get constant is output. Now we have to compare this with this one, isn't it? No, this with this one. Y of minus L is equal to, what is boundary condition 1? Y of L minus L is equal to Y of L. So minus C1L plus C2 is equal to C1L plus C2. C2 can be cancelled on both sides. You will get negative 2C1L, or 2C1L is equal to 0. This gives C1 is 0, not C2. C1 is 0. Okay. And second boundary condition. These two are equal. That will give you y prime of minus L is equal to y prime of L. C1 is equal to C1. There is nothing. C1 is equal to, so the only result is C1 is 0, not about C2. So in the equation, in the solution, we substitute C1 is 0 here. Therefore, what is your y? Y is C2, because C1 is 0, we get C2 is a non-trivial solution which is an eigen function. Therefore, lambda is 0 is an eigenvalue. So lambda equals 0 is done. Now lambda is greater than 0. See, y is equal to C2 is an eigenvalue, eigenfunction. So C2 can be chosen as 1. Therefore, first element in the set, we have been given a set 1 cosine series and a sine series, isn't it? 1. Why you can choose constant C2 is 1. So first term has been done. Next we are going for lambda greater than 0. Let lambda is positive mu square. Therefore, the differential equation will be y double dash plus mu square is y equal to 0. And the solution, we don't want to repeat the procedure, same. C1 cosine mu x plus C2 sine mu x. This is, we are going to use all the boundary conditions. So for boundary condition 1, we will go ahead with y of L. Substitute x is equal to L. In this equation, I will get C1 cosine mu L plus C2 sine mu L. Similarly, y of negative L. C1 cosine is an even function. Negative inside will not be a troublesome. Mu L cosine mu L. But sine is an odd function. Negative comes outside. C2 sine mu L. Now equate them. First term is y of L should be equal to y of minus L for the boundary condition 1. Y of L, the left side is C1 cosine mu L plus C2 sine mu L is equal to C1 cosine mu L minus C2 sine mu L. Same terms can be removed, isn't it? So first term and first term can be cancelled. This first term is positive, this is negative, C2. So what do you get? On the next page, you will simplify it. When you take this term to the left, you get it to it will be positive, so 2 times C2. So it will give 2 times C2 sine mu L is equal to 0. So what you get is this one. So we get this conclusion. We don't know what is the status of C1, isn't it? Just we conclude that if C1 is 0, then C2 should not be 0. Therefore, this should be the answer. Sin C2 could not be 0. Therefore, the product of these two should be 0. Therefore, this gives sin mu L should be 0. Because here only two possible. Either C2 is 0 or C2 is non-zero, isn't it? If C2 is 0, there is nothing. We will write off the cases eigenfunction. But if C2 is non-zero, there is a possibility. Sin can be 0. Sin mu L is equal to 0. We know only sin n pi is 0 for all n values of integers, isn't it? Therefore, mu L is equal to n pi. Therefore, mu is equal to n pi over L. But we know mu square is lambda. So, lambda is mu square, which is n square pi square over L square. So, for these values, which sign will be 0, that will be giving you some non-trivial solution. Therefore, the eigenfunction C1 is 0, then only second part of y is, I should repeat y, C1 cosine mu x plus C2 sin mu x. But C1, we assumed C1 is 0, C2 non-zero. Then what is happening here? Y, first part is 0, second part is C2 sin mu is n pi. Mu is n pi x over L. This is an eigenfunction. An eigenfunction for the eigenvalues. This is our lambda, which is pi square n square pi square divided by L square. And when you generalize this one, it is y, and when you take it C2 is 1 sin n pi x over L. And we have done this is only for boundary condition 1. We have to do the same with the boundary condition 2 to get another set of functions. So this is our yn second solution. First case gave you constant, second case give you sin n pi x by L. Third, no, actually this is the third case. First case, there is a lambda less than 0, there is no eigenvalue. Lambda equal to 0, you got y is constant. Lambda greater than 0, there are two possibilities. One is boundary condition 1, second is boundary condition 2. What is boundary condition 2? Dealing with y prime. Y prime of negative L is equal to y of L. What is y prime? Differentiate y minus C1 mu sin mu x plus C2 mu cosine mu x, and y of y prime of L. Substitute x is equal to L minus C1 mu sin mu L plus C2 mu cosine mu L, isn't it? Y prime of negative L, this will be positive. C1 mu sin mu L plus C2 mu cosine mu L, because sin will give negative outside, so it will be a positive outside. Cosine will constitute the negative. So when you substitute this in this result, what do you get? Y prime of minus L. There should be minus L. No, y prime of minus L is equal to y prime of L. C1 mu sin mu L plus C2 mu cosine mu L in the left side is equal to y of L, y prime of L, minus C1 mu sin mu L. Plus C2 mu cosine mu L. Okay, further you can say that this one and this one can be cancelled. You will get, when you take this one to the left side, you will get 2C1 sin mu L is equal to 0, isn't it? So here we assume if C2, in the previous case we assumed C1 equal to 0. Here if C2 is 0, then C1 not equal to 0. This gives sin mu L should be 0, isn't it? C1 not equal to 0. This gives sin mu L is equal to 0. This implies mu L is equal to n pi, mu is equal to n pi over L. So lambda is equal to mu square, which is n square pi square over L square, isn't it? Therefore C1 not equal to 0 here we assumed. In the equation of y, put y2 equal to 0, C2 is 0, y C1 is non-zero. So y is C1 cosine mu x plus 0, where y is equal to C1 cosine mu is n pi x over L, is an eigenfunction for the eigenvalues lambda is n square pi square over L square. When you take C1 is C1, yn, generalize it, yn is cosine n pi x over L is yet another eigenfunctions. For all n 1, 2, 3, 4 you can choose. So we have proved the collection of all 1 sin n pi x over L cosine n pi x over L, where n is 1, 2, 3, 4 is the solution of the solution of the period, boundary value problem, that is Sturm Liouville boundary value problem. Is the eigenfunctions of the given boundary value problem, Sturm Liouville, isn't it? Okay, we have already proved they are pairwise orthogonal in the previous chapters. So that's the end of this problem, problem number 3. One more problem which is given here. The solutions are given here for the previous problem. This is the last problem. First thing is I have to verify this, put this differential equation in self-adjoint form, simplifying the first two steps. Given orthogonality relation, okay, this kind of differential equation is called Cauchy-Euler differential equation. First we will put it in self-adjoint form. Divide this equation by x. What you get? What you get is x y double dash plus y dash plus lambda times y over x is equal to 0. Now using product rule we can write this one as x y prime the whole prime, isn't it? And choosing this one as p, this one as p, lambda p, where p is equal to y over x. This becomes self-adjoint form. This is Sturm Liouville boundary value problem, and this is self-adjoint form. Adjoint form, right? Okay. That is now r is equal to x. So r y prime whole prime plus p lambda. Okay, p lambda y. P lambda y. Actually, lambda p can be taken as 1 by x. P is 1 by x. P lambda y. Okay, this will be the self-adjoint form of the given differential equation. And we are done with B. We have to find the eigenfunctions. And orthogonality, we can at the end we can check the integration of the functions. Now let me go to the separate sheet. Okay. I would like to write the problem again here. Given is x square y double dash plus x y dash plus lambda y is equal to 0. Boundary conditions are y of 1 is 0 and y of 5 is 0. So we know the lower limit is 1 and the upper limit is 5. Okay, now we should be careful about converting this into this is a differential equation of variable coefficients, isn't it? We have to convert it to constant coefficient case. Let x is an e raised to z, a new variable we are introducing. So dx over dz will be again e raised to z. What is the formula for dy by dx? This is dy over dz and dz over dx. What is dz over dx? When x is e power z, we know ln x will be z. So when you differentiate z with respect to x, dou z by dou x, it will be 1 over x. We can use this one here. Dy by, if d is d by dx, we can take theta as d by dz. So wherever this is d by dz, this term, therefore dy by dz can be theta times y. I write here theta y, and this is 1 over x found here, isn't it? That is this one. That is y prime, which is dy, can be written as 1 over x theta y. And what about the second derivation? That is x dy. We can further define this as x square d square y is equal to theta into theta minus 1 y. You can check this one and it will go right. So I'm going to use this one. You might have studied this one in the elements of differential equation, this conversion formulas. So this one will be used in the given equation. Therefore equation number 1 becomes x, this is first term is x square d square y. It will be theta into theta minus 1 y. Second is actually when you multiply this x to the left, actually what you get here, x into dy is equal to theta y. So x into dy is this term, is theta y plus lambda y is 0. When you simplify this one, theta square minus theta y, theta will be cancelled. This will be theta square plus lambda times y is 0. This is the new differential equation where theta is a differentiable with respect to differentiation with respect to z, isn't it? A new differential equation. Now we are writing this one as our new equation where theta square y plus lambda y is 0. Now there are three cases. First case, lambda less than 0, let lambda is negative mu square, so theta square minus mu square y is equal to 0. The auxiliary equation you can find, and the solution will be in z. Y is c1 into mu z plus c2 into minus mu z, but we know z is e power x, isn't it? Z is so e power z is x. This can be further written as c1 e power z to the power mu plus c2 e power z to the power mu. So y is c1 into x power mu, c2 into x power minus mu. This is the result, and here boundary conditions should be recalled. What are the boundary conditions in the previous page given? Y of 1 is 0, y of 1 is 0, and y of 5 is also 0, isn't it? Y of 1 is 0, y of 5 is 0. Both are in y. So y of 1 is 0. Put gives, this is boundary condition 1, this is boundary condition 2. So here again I repeat here, since this y of 1 is 0 gives this one, y of 5 gives this one. So when you write this as a matrix form, you get 1 1 for c1 c2 and 5 power mu, 5 power minus mu. So here this determinant is non-zero, therefore c1 c2 should be 0. C1 c2 should be 0, therefore this is a trivial solution. Here y equal to 0 will be the answer. This is a trivial solution, so lambda negative is not an eigenvalue. So when lambda is 0, this will be the equation, differential equation, lambda part will be 0, whose solution is this one. But z should be replaced by ln x, isn't it? And substitute the first boundary condition, y of 1 equal to 0. Ln 1 will be 0, so this part will be 0. C2, which is equal to 0. C2 is 0. Why? Because first boundary condition is equal to 0. So when you substitute x equal to 1, this part is equal to 0, so C2 is 0. And second boundary condition, y of 5 equal to 0. When you substitute x equal to 5, C1 ln 5 plus already C2 is 0. So C1 ln 5 should be 0. ln 5 is constant, so C1 should be 0. So we get C1 and C2 both are zeros. Therefore, one general solution y is also solution 0, which is a trivial solution. So y lambda is equal to 0 is not an eigenvalue. Third case, we are in third case, lambda greater than 0. Now we take lambda equal to mu square. This is the form of differential equation now. The general solution has been given here, c1 cosine mu z plus c2 sin mu z, and substitute, so z value should be converted into x, substitute c that one, so c1 cosine mu lambda x ln x, c2 sin mu ln x, z has been replaced, z is ln x, we know. Okay, now first boundary condition gives this term ln 1 is 0, so cosine 0 is 1, c1 will be there but c2 is 0. C1 plus C2, C2 is 0 is equal to 0. So C1 is 0 is the conclusion from first boundary condition. Y of 5 is 0 gives C1 is already 0, so first term is 0. C2 times sin mu ln phi, this equal to 0, isn't it? This equal to 0. So we know only C1 is 0, C2 may not be 0, isn't it? So C2 not equal to 0 gives, if you want C2 not equal to 0, sin part should be 0. So sin mu ln phi should be equal to 0. So this part should be equal to n pi. Mu times ln phi is equal to n pi. Therefore mu is equal to n pi over ln phi. Mu is our lambda. Lambda is mu square. So n square pi square ln phi whole square will be the lambda eigenvalue, for which the first, here we got C1 is 0 but not C2, isn't it? So what is the final answer? Y is equal to, C first part is 0, second part is C2 sin mu ln phi, isn't it? Mu is root of lambda. C2 sin root lambda ln phi. Ln x in the differential equation, it's ln x, isn't it? Because we have to take from the solution, y is equal to C1 mu cosine mu ln x plus C2 sin mu ln x, that is the y. Check back. So from the C1 is 0, you'll get C2 this one. So generalize it. ym is C2 sin root phi ln x is an eigen function for the lambda value. This is actually mu is a root lambda. So the lambda value n square pi square by ln phi whole square. So this we have proved the eigen functions. Now verification of orthogonality. Integral a to b p of x yn of x ym of x dx should be 0. And here what is p value? Here p of x you can check in this form. Actually in the self adjoint form we have seen p of x is 1 by x, so we can write a to b, p of x is 1 by x, which is sin n pi x pi ln x over ln phi, sin m pi ln x over ln phi dx. You can simply verify this one is 0 by using the previous chapter's method. By substitution method you can choose u is ln x, then du will be 1 by x dx, and then you can convert everything into u. The limits, this limit will be from 1 to infinity. Try this part yourself, right? Okay, thank you very much. That's the end of this problem.